here to honor Daron Acemoglu. I have to confess that I am myself very honored to have been chosen to honor you. So I thank the organizer for that. Daron Acemoglu has many skills, and one that has not been mentioned yet is that he's an amazing textbook writer. And he wrote a masterpiece, a chef-d'œuvre, a monument. It's a good weapon. It's a very good textbook concerning modern economic growth for graduate students. But in these textbooks, there are some technical chapters giving the principal notion in dynamic optimization that are necessary to make intertemporal choice, and intertemporal choice is the backbone of macroeconomics and many other fields in economics. And in practice, there are two of those technical chapters, Chapter 6 concerning dynamic programming and Chapter 7 concerning optimal control theory. In fact, in this talk, I will settle some questions concerning time consistency, and I will use a theory of optimal control. Most of the literature in macroeconomics, starting from Leibson, use dynamic programming because they introduce time inconsistent preference into models in which there are shocks at each period. And for those kind of models, dynamic programming is a much better tool. But when you talk about time consistency, you will test for agents changing their plan. In a model with shocks, a rational agent, it's the initial idea of Robert Hall, have to change at every period to take into account the new information. And I want to test for time consistency without this noise, and so I will put all uncertainty out of the model, and thus I can use optimal control in continuous time. That is, I think, a much powerful and maybe insightful way to modelize this problem. So what are we doing today in this talk? Basically, I will do macroeconomics with exotic preference. I will put in standard macroeconomic model some exotic preference. Is it behavioral economics? Behavioral economics try to found a more accurate economic reasoning relying on more realistic psychology assumption. I don't share Colin Kammerer's mechanic definition of behavioral economics, but certainly my work is concerned behavioral economics. But what is characteristic of, in practice, a behavioral model is that it relies heavily on ad hoc methodology. You take a special form of preference, quasi-hyperbolic discounting, known to implying time inconsistency, and you show that it allows to explain many empirical paradoxes. I have nothing against ad hoc methodology because for discovering a new continent, for the research for new ID, it's a very good tool. But my concern is more fundamental, and I define fundamental macroeconomics like this. I will start by generalizing a standard model, and each existent model will be a special case of my general model. And doing so, it offers a synthetic and deeper understanding of the whole domain of intertemporal choice, I hope so, and the way it interacts with macroeconomic phenomena. So I don't want to show that if you take this special utility function, you can explain something. I want to give you a map. If you innovate, inventing a new way to model intertemporal choice, I will give you a criteria to know if your model accounts of the behavior of a rational agent or not. And it's an important question, because if agents are not fully rational, the way to do economic policy is not exactly the same. There is a very good book by Gilles Saint-Paul about this kind of question. So The starting point is the exponential discounting model given by Samuelson before the World War II. So in this model, it's intertemporally additive. It can be written as a sum or an integral in continuous time. It multiplicatively separates discounting from per period utility, and we are all trained with this idea that we have something that is a discount function, and discounting is captured by one parameter that is constant, invariable with time or with the level of consumption. If you look for the foundation of this model, there are two foundations. Stationarity, introduced by Koopmans and axiomatized in a simple setting by Fishburne and Rubinstein. Stationarity means that if you postpone, you have the choice between two consumption streams, and if you postpone both consumption streams by the same duration, your choice is not modified. And as shown by Koopmans, if you have additivity and stationarity, you will have exponential discounting. And there is another approach by Strotz showing in 1956 that this model accounts for time consistency, and Strotz proved that only models with exponential discounting are time consistent. The result of Strotz is true, but I will show you that the understanding of the result of Strotz can be misleading, and I want to clarify this point. Yes?
Well, the big hypothesis for me is the theta. You say that...
No, but I will drop... Yes, I will drop that. No, don't worry. There are two... The problem is that there are two methodologies. Stationarity decision theorists think a lot about stationarity, so the methodology is axiomatic. And Strotz is a paper with calculus of variation and its dynamic optimization. And both fields are very mathematical, but it's not exactly the same mathematics. And I think because of that, there have been some misunderstanding. Does time consistency imply stationarity? Does stationarity imply time consistency? 10 years ago, it was very obscure even for very top level economists. And in fact, none of these propositions are true, and it has been proven by Alevi, published in Econometrica in an axiomatic paper, who disintegrates clearly for the first time the notion of stationarity from the notion of time consistency. That's the axiom. Don't spend too much time to understand the axiom because I will go quickly. But the important idea is that there are three axioms: stationarity, time invariance, and time consistency. The new axiom in Alevi is time invariance. And what Alevi show is that if two of the axiom is true, then the third is necessarily true.
What is time invariance? I understand stationarity.
So the idea is you can make the date of consumption to vary, the date of decision to vary, and the distinction between the three is they are not varying the same way between the axioms. So the point is, if you take a corollary of this theorem, it means that if one of the axioms is fulfilled, but another of the two remaining is not fulfilled, then the third will not be fulfilled. So it is possible to have intertemporal time preference that are non-stationary but fully time consistent, and intertemporal choice that is time consistent but not stationary. So the idea was to see that there was in fact three ways to modify a decision through time. So Alevi do that within the axiomatic framework. And I will try to disentangle the two notions, but on the side of a dynamic optimization. So for a long time, exponential discounting have many, does not always fit the data and things like that. So economists were dissatisfied with the model. So a first stream of literature decided to drop additivity and to keep stationarity and to have a recursive utility function that works well with dynamic programming. And in fact, I will take the opposite way of thinking. I will keep additivity. I will drop stationarity. As Fishburne and Rubinstein says, there are no reason to believe that stationarity is an axiom of rationality. Time consistency is an axiom of rationality, so there is no cost of dropping stationarity. Additivity is not an axiom of rationality either, but additivity provides models that are very tractable. So by keeping additivity, I try to work with models that are tractable. So I will discuss time consistency, and I will use optimal control theory. So what I'm going to do, I will search in a big set of intertemporal utility functional, the one that are time consistent. So what I wrote is just, the set is a capital script V. Of all the functions that can be written like that is the sum from minus t, the decision date, until capital T, the time horizon, of a per period felicity function that depends on the consumption at any age. S is varying under the integral, so it's the age of consumption. And this function V can vary with C of S, with S, and also with the decision date. Okay, so it's very simple. It's the most general model of additive intertemporal utility function. So a problem is I suppressed time discounting, so we are used to use a discount factor and discount rate. So what can we do? I will show you that we can retrieve those concepts in my general setting. I will characterize the subset of the time-consistent intertemporal utility function. So I will write them TC of capital strip V of T. And finally, I will finish with some consideration for non-time-consistent agent. What is important for me is to give a clear boundaries between time-consistent and time-inconsistency. Not give you example of time-consistent utility functional or time-inconsistent utility functional, but to give you a criteria that give a complete mapping of the various models that exist or that can be invented in the future. So now I will address the problem of the marginal, the discount factor. I'll go back simply to the Fisherian definition of the discount factor. In Fisher, there is no additive separability, so the definition is very general. And the discount factor is just the marginal rate of substitution between the same level of consumption at two different dates. So the time distance between the two dates is tau. And what I will just say is that is exponential of minus theta tau, theta being the rate of time discounting, but that will be allowed to vary according to C, according to S, according to tau, and according to T, the decision date. So I just write the definition. It's a marginal rate of substitution. And I take the limit of that, first order Taylor expansion, when tau is going to 0. And what we obtain is the most general definition of the instantaneous rate of discount. That is, it is at the denominator, it's the marginal felicity function of consumption. You derive according to the first variable. And at the denominator, it's the second order cross derivative. You derive first time according to consumption and second time according to age. So it's the derivative of marginal felicity of consumption according to age. This definition is very general and includes all the definition we know. If you put a model that you know with this definition, you will find the proper rate of discount. So what we obtain, it is a rate of discount that can vary with C, vary with S, and even vary with the decision date.
So S is the actual date when consumption is realized.
Yes.
T is the decision date.
Exactly. In the utility function that I don't make the comment before, and it's a mistake, your felicity function can vary with H, with S. It's anticipated. This variation includes the idea of discounting that is hidden in the formulation, and includes also the idea of changing taste with age. Age people have not necessarily the same per period utility function than young people. And it changes also with T, and I will work with naive agents. So naive agents don't understand that at different decision dates they will change their mind and decide something else. That's more standard definition of absolute resistance to intertemporal substitution or risk aversion, but there is no risk in the model. And what is very important to notice is the symmetry between the two definitions. And this symmetry gives a structure that will be important and determine some of our general results I will show you after. So the program of the agent is to maximize, to find the function C that maximizes the intertemporal utility functional under constraint. Here I make things simple. You have a capital that brings interest at a constant rate R, and you use it for consumption. I work with finite horizon because I believe in finite horizon. I came from overlapping generation, so I'm interested in that subject. And also in my reasoning, transversality condition will be very important. And transversality conditions are much easier to derive with a finite horizon. If you don't understand why, read the chapter 7 of Drouhin's book, and you will understand a topic that is very difficult and that Drouhin make understandable for the common of the mortal. Makes understandable. So if we characterize the model, we are happy to find that the derivative of consumption according to time respect the standard property, the rate of interest minus the subjective rate of discounting over the rate of resistance to intertemporal substitution. The only difference is know that the rate of discount is the general definition useful in a general model. Okay, so now let's introduce dynamic consistency.
Just to understand the notation.
Yes.
So in the previous slide, so CTS means my time plan at time t for how much consumption is going to change at time s.
Yes, exactly.
And so far there is no time consistency, so this does not need to be constant in t.
We will address this question now. So C is the consumption decided at date t for every future age s.
But what I'm having a hard time understanding a little bit now that you've gone to the optimization is, if there is no time consistency according to this definition, is the agent making mistakes about his future plans? How is that working out?
He makes mistake because he don't anticipate that he will change his mind. So.
Well, that's a bit, that's a little bit. There's a tension because
yes.
he's doing the dynamic optimization.
Yes.
He knows everything.
Yes.
But he's still making sort of inconsistent. I mean, this doesn't arise when we have the time consistency. But
yes.
But in the not time inconsistency case, he's still making inconsistent plans in some sense.
Yes.
I mean, the sort of the recursive method sort of was imposing that it's going to be consistent plan. At least the sort of the Storz, Harris, Leibson version.
Yes, but first of all, it's the same methodology as Strauch, who introduced the notion. And second, I think that in the introduction of Peleg and Yahari paper in the 70s, Yari make a very clear statement of the strange character of thinking about time consistency. And I'm not sure that modern literature escaped from this strangity, or I don't know how to, but maybe I can move on. And
it's related to what O'Donoghue and Raven call naive.
Yes, it's naive. It's naive, but I think sophisticated. I will address this point in the end of the talk. So now, suppose that at date t prime, after date t, you are allowed to plan again. So you will solve this problem. And what connects the two problems is that the capital, starting capital at that t prime will be the capital at that t prime resulting from the preceding planification of the agent. An agent will be time consistent if the consumption at that S within both for both agents, for each planning date will be the same. And in this case, you are time consistent. A necessary condition for time consistency, of course, if the two consumption streams are equal on an interval, if we are equal only on one point, it will not be true, but because when the two consumption streams are equal over the interval, we have this necessary condition for time consistency. So that's if we develop, we have something like that. And in fact, it's a system of two partial differential equations. We have also a constraint that we can integrate, and we use the transversality condition for that. And both consumption streams will respect the intertemporal constraint, so they will have the same integral on the interval. So when two functions have the same derivative on an interval and also the same integral, they are equal, so the necessary condition is also a sufficient condition. So I solve, I make the demonstration, I'll solve the partial differential equation, and I obtain this result. The three statements are equivalent, the agent is time consistent, and the function phi is of the form alpha t times w of a function that depends only on c and s, plus a function that depends on t and s. Alpha can be any function, gamma can be any function, and w can be any function. If you put that on an integral, you can see that alpha t is a constant for the program, and gamma will be a constant. So in fact, what we have here is just linear transformation of a utility. It means that any function that can vary with h without varying, without introducing t in a sophisticated manner in the integral implies time consistency. And the last point is this one. It's equivalent with having the coefficient of risk aversion and the coefficient, the rate of time preference that does not depend on t. Okay. So in the literature, there are a lot of people, including some that published in very high, that believe in Strott's result, and there are other economists that they know that you can have something else than exponential discounting. And for example, in a literary statement in Gilles Saint-Paul's book in 2011, he gives this property, and there are papers by Becker that gives also this property, but it is always literary. In my paper, I think I'm the first one to provide a general.
So in particular, what Andre was asking is a lot, which is a discount, exponential discount rate that changes over time is fun.
Yes, yes. But discount rate that vary over time can give you any function, in fact, almost any function. I will give you some example because it's not clear in the literature, and I have to understand why. And to understand why, I will give you some example. So now we start from a simple case. We are searching into the set of functions that can be written like that. We have a multiplicative separability between a discount factor that depends on algebraic time distance, a sum, and with a utility function that is invariant. Okay? If we applied our general statement to this function, we should have, in fact, multiplicative separability between what depends on t and what depends on s. And the only function of difference between s and t that is also multiplicatively separable, it's the exponential. So if we search in this set of utility functions, it's true that only exponential discounting with a constant rate is time consistent. Every other possibility are not time consistent. So that it's the model of Samuelson, not the proof of Samuelson, and that corresponds to conventional wisdom. Now, if we search in a model like this one, it's not f is the discount factor is not a function of s minus t, but it's marginal function of s and t. And this result is already published by Burness in 1976, but received less than 30 quotation. But what Burness proves is that you should have for the discount factor multiplicative separability in T and S, which is a special case of my general model, but captures the same idea. Yes. And what is funny is that we can have some kind of hyperbolic discounting. It's not quasi-hyperbolic discounting. That is time consistent. If you take a discount factor that is T over S, it's decreasing, the discount factor. The discount rate will be 1 over S. It's not constant, but decreasing. And you will be time consistent because you have multiplicative separability. And what is very funny is that Hensley, the psychiatrist that makes some experiments on pigeons, the first function he took to assess the fact that pigeons were irrational, it was to proposing this function, this hyperbolic function, as describing the property, the behavior of the pigeon. But he misunderstood the result of Schwartz, and in fact, when you regress with that function, you will have a time-consistent pigeon, as you can have time-consistent humans. You can have also other examples, for example, people that will change his mind according to season, and if you have that, you will be completely time-consistent. Maybe you prefer to consume in summer than in winter, and it's rational to do that.
So can I ask?
Yes?
I think these results are very interesting, but I'm having one other small problem, which is once you add uncertainty, it's not clear that they will all hold, because the Jensen's inequality might come in different ways with uncertainty. So can we generalize this in some way?
My idea, but maybe I'm wrong, is that we have to isolate time consistency without uncertainty, and it will work with uncertainty. If you say me that it's not necessarily true, I have to look at that.
I'm not saying it's not true. You say it's true.
Not necessarily.
I was just worried that, my expectations of different things as time goes by might interfere. Not in this case, but when the case where it's U of C comma S. So that it's sort of S becomes the expectations and S gets
What I can answer to you, it's in the paper of Burness, it's a paper with uncertain lifetime. And I have a paper published in Journal of Economic Dynamics and Control where I make the same reasoning, but with uncertain lifetime and rank-dependent transformation of the probability of uncertain lifetime. So for this kind of uncertainty, it works. But
uncertainty, for example, which is the case that many of these papers, more applied macro consumption papers are worrying about, for example.
I have to
Next
think
paper.
about that.
Next paper.
And finally, the last example, and it's an important one because it's precisely the one of Strauss. Strauss search time-consistent intertemporal utility functional within this set of functions. And there is a discount factor that depends on the time distance, but utility is also varying with age. And if you apply the result, my result, you first statement is say, yeah, it's necessary to have f to be exponential. But the function u can be any function, so it can also have an exponential in it. And if it has the just inverse exponential of the one is before, it will disappear. So, in fact, my result is not more general than the result of Strauss, is only the result. It's not more general, but it allows to understand that there is a misunderstanding, there is a kind of fallacy of composition in Strauss result. So I advance quickly. If you think at paradox, and you can say the model is very general, it's too general, so we can put some supplementary assumption to account from empirical evidence. If you have some empirical evidence coming from experimental economics. For example, there is a common difference effect. Theta is varying experimentally. Some experimenters find that theta is varying with S. But it does not mean that you are non-rational. So you can have this result with rational. And if you do the math, it's very simple. It's just implicit derivation. You can show that you should have this condition. So it implies the third order derivative. And this condition is very similar to the one given by Kimball for precautionary saving, except that in our model we have two variables in the utility function. So the third order derivative can be according to either one or other variable. We have the same thing for the absolute magnitude effect, that the rate of discounting can vary with consumption. But what is more important, because we have a structure that both rho, the rate of risk aversion, and theta, the rate of time preference, are a second order derivative of the same, depends on the second order derivative of same function, we will necessarily have that the absolute magnitude effect, meaning that theta varies with C, implies that risk aversion will vary with age. And I think it's an interesting result because there are a lot of literature in finance to understand how per period risk aversion will vary with age. If we have a model that is coherent, we should have this symmetry in the properties. So that's the evidence from experimental economics. We can also have evidence from consumption theory. So it's well known that the consumption stream is M-shaped. Generally, it's explained because of Boring constraint in model of precautionary saving. But you can also explain the discount, the M-shape of consumption, noting that the time preference is determined partially by your probability of dying. The hazard.
That's very consistent with the data, and the way that previous literature deals with it is a little inconsistent because if you look at the papers by Blundell, Banks,
Yes.
Atanasio, they do allow consumption to be a function of age and
Yes.
demographic characteristics, but they take those out and then apply sort of additive models to the remainder in some sense. But that would be sort of inconsistent, so this is saying that you can just do optimization taking those changes into account.
Yes, exactly.
So there's fairly good evidence that that you need sort of those age effects if you want to match.
Yes. one of my main ideas is in a graying population, you have to investigate more precisely the effect of age on your consumption stream, and to see if you need to, you can expand the possibilities for working on that. If you do that, you will have a theta that will increase with S. It's the opposite result than the experimental result. And if you take a second order derivative of this, you will have some interesting effects. So you will have a hump that will be determined by this. But when you are on the side, when you are very young and not very young, you will have those effects. That's the interaction between the slope and risk aversion and things like that. The rest of the paper, I try to characterize for an agent that is not time consistent, the effective consumption program. So the planned consumption profile will be that, but the problem is that you never observe the planned consumption profile because agents always change their mind. So from an empirical point of view, and I think it's the reason why agent invented this idea of sophistication, because it can give you a methodology to find something that is observable. But you can deal with the problem, and I think I give some result for that. So the only thing that can be observed in the planned consumption profile is the starting point. So you can define for an agent that is continuously replanning, you can define an effective consumption profile that will be constructed as the initial point of any planned consumption profile, and that's what I do here. And because we have formalized in the model the starting point of consumption using the transversality condition, we can explicit. It's not totally explicit because CT is on both sides of the equality, so it's an implicit definition in the general case. And we can do a second order, you can differentiate this to express the difference between the rate of growth of the consumption profile and the rate of growth of the planned consumption profile. And the difference between both is given by this ugly term. But this ugly term is not so ugly because exponential is always positive, so the sign will depend on this factor here. And if agents are present bias, which is the common assumption about non-consistent agent, we can prove that with all generality, so if I parameterize using a Barrow 1999 quasi-hyperbolic function in continuous time, I can draw, and there are some properties that are in the paper. So that's the planned consumption at age 20, that's the effective consumption, so they share 1 point in common. But what I show in the paper, and I think it's not in the literature, that there will be one crossing property, always, because of the intertemporal budgetary constraint. And there is also an horizon effect. As you come close to the end, the difference between those two slopes vanish because it's an integral depending on the decision date and the horizon. And at the limit, when you die, there is no more slope because there is only 1 point. But when you die, the two slopes are the same. So I think I give some more insight about the observable behavior of a naive agent. I'm finished.
Well, thank you.
No, it's nothing. It's just conclusion.
So, do you have any questions? Yes,
Can I ask one more question?
So,
But it seems like, you should, it's not an easy problem, but it would be nice to sort of develop what the right optimal control approach would be when these people are sophisticated. I mean, in some sense, the time consistent part is totally fine, but for the timing consistent path, you don't necessarily want to say they're going to be fully naive, and, so at least in the recursive case, at least that's easy how to do that. In the optimal control case, it's not, because you have to put an endogenous constraint somehow.
But there is a paper by Pollack in 1968, and he do that. He compares in continuous time. There are not many reflections on that in continuous time, and the agent is allowed to plan at a finite number of a period. And he looks at what happens if you plan constantly. And I think, I hope that I'm not wrong, but I will verify, that in this case, there is a problem with the sophisticated agent, and you cannot solve the sophisticated agent when an agent is constantly replanning.
I didn't know this paper, but it's just hard to think.
But when he's naive, I think it works. And I think the idea that people are naive seems to me a better, I believe more in this assumption than the other, because you are not rational, but you are sophisticated, and you try to force your future self to behave like you want now. I believe much more in the approach of Bernheim and Wrangel. When you are not rational, you know that you are not rational, and you try to avoid, not to impose your will to your future self, but to impose to your present self something that is beneficial for your future self. And I believe more in that approach.